Hello and welcome back to Compiler Programming. Today I want to do something a bit different from the usual programming. A couple of days ago I decided to try and test how the compiler behaves doing compile time execution in relation to some other ones. In particular, I checked out C++ and Zig. Would love to try out Jai, but I don't have access to that just yet. So I only have these three, and as one would expect on a test where I'm just counting from 0 to a million, the compiler does amazingly well. But we also have this test of constant folding, which is not really compile time evaluation, but it is roughly in the same category. And what happens here is that I have 1,000 definitions, each of them doing 1 plus 1 plus 1 1,000 times, and then we are summing all of those 1,000 definitions. The reason they are spread like that and it's not long one long expression is because it would actually kill some of the parsers, and also this way we are stressing out the variable lookup and some other things. So I think this is a pretty decent setup. And here, Clang absolutely destroys everybody else. It has a pretty bad startup time, but the actual constant folding is very, very fast. Originally, this time was very bad. I took some steps yesterday to improve it, but there is still lots to be done. And so what I want to do today is do a bit more profiling and see what we can do to make this number go down a bit. First, let's replicate it. Since I'm streaming, it might be, or since I'm recording, it might be a bit higher than what it was before, but we can at least check what it is right now. So we have a new baseline. I will need to compile it with OX so that we have a release build that will take a bit of time to actually compile, but from there we can try and see what the score is, and then we will try out the Visual Studio profiler, maybe add some profiling ourselves and see what can be done to improve this stuff. Okay, now almost there, and we are done. Okay, and this is the command I'm using to measure this stuff, and we can try to run it and see what it will say. Yeah, as I expected, the time is slightly worse than what I had without recording, but it is in the same ballpark. Good. Now we will get to here, which is Visual Studio, and Visual Studio actually has a profiler built in, which I do not see at the moment. Show diagnostic tools. Yeah, I think that is what I want. Let's try to run it and see what's going to happen. I have unnecessary stuff. We are recording CPU profile, which is good. And we should be able to see that profile in here. But there is not much to check because our tests are very, very fast, and we would need to actually have something that is much slower. So let's make a copy of this hello world test that will try to compile our compile time benchmark. Okay, it uses dashes for name, so compile time benchmark, and then the name of it is folding. The rest I think is exactly the same way. I will also change it from it to fit, which is like focus. So only this test will actually run now from the whole test suite. And I think that's about all that we need. If everything goes right, now we shall see where we are spending time. Now, MSVC will actually run debug build, so we have all the symbols and whatever, so it will be slower than the real one. And profiling debug builds is a bit tricky because a lot of the time will be spent in various debug assertions and checks and so on and so forth. So we'll have to be careful with how we approach this, but let's check this out. As you can see here, it also takes a lot of memory to do this, and that actually might be one of the big reasons why it takes so long. Memory allocation, even if it is an arena allocation, is still takes some time, so we have to look at that. Okay, so we have our profile and we can check what it says to us. Right, so it says that a lot of time is spent in scope map get by hash internal. That is not very good. We cannot really even look into that because it's a template. I think the only way really to look inside and see what is happening there would be for me to actually manually inline that template into code here and go from there. Now we'll see if that's what we will want to do. But we can also look at some other suspects. Now, one very suspicious thing here is that we're also spending 200 milliseconds in some external code that is quite interesting, I would say. And we also spend 245 milliseconds inside of value make internal. And this is actually what I want to look at, because that means that we are creating a lot of values, and we are also we are allocating that memory. You can see here that we're also spending 268 milliseconds just allocating that memory. Neither of these things is very good. And even for hashing, one thing that we definitely can do is to store so as you can see here, we also spend 1% of time in hash slice, and this is something we can definitely improve. We can pre-hash the symbols, and we could send that hash directly to the lookup. So I guess what I want to start with is allocation, and I even already know a code that is likely the cause of a lot of allocation here. That is in here where we have token handle operator. So actually maybe not this one. Token dispatch operator. Where are you? Right. Wait, that is also not the one. It is this one. It is Eval Operator. Okay. So what's happening here is the main dispatch loop for built-in things that we have, built-in operators, built-in functions, and so on and so forth. And it's not a very well optimized function at all. We do slice equality all over the place, and in general case that's not too bad because it will check for the length first, and if the lengths don't match, it doesn't actually do memcompare. Memcompare itself is also pretty fast, so that it's not too bad but not too good either, especially considering that we have more than 1 million pluses in the program, and the fact that we have 1 million pluses and we have to look them up as operators is also accounting for and the reason we see the hashing so high up here. Anyhow, let's look at what's happening in here and go from there. So I think a big source of allocations is this stuff. The idea of value any is something that I learned when I was implementing the Hindley-Milner type inference. The idea is you have this variable that can, or this value that can be of any type, but once you assign a type to it, it stays that type. And we are using it not in the very best way. We are just using it as sort of out value. So let me show you. We have this assignment code, and this assignment code does the following. If it detects that the target value of an assignment, so if you have something like x is 42, and if it checks if x is this special any value, then it just copies the descriptor, storage, and overloads to that value, and that's it. It doesn't produce any special code. And this is how that works. But we are obviously creating a lot of them. Well, to be precise, we create 2 here, and let me mark this so I don't forget. And we also create 1 over here. And it would be very nice if we didn't. There is actually no really reason to create them on a heap because they never leave this function. So we are creating them and then they're just sort of stuck there. And this is why we see that big memory growth. I think there are other contributors, but this is one of them. So at the very end, can we like see somehow what is the actual value of the memory? Well, it is somewhat okay. Yeah, so this is 1 gigabyte. It's not very precise, but I guess that will do for now. We want this to look slightly better. This is what we're going to do. And let's start with this one. The idea is that I'm gonna take value any, and I'm gonna slightly change how it's implemented. Or maybe rather, I will create a version of it that does not allocate. So let me look at what this does. Combine source location, context, storage any, and source range. Okay. Let's look at value init, and then we can go from there. So I can have value any init, and that would be this, compare the source location. It doesn't want the context. It wants an epoch, and this is actually quite tricky because we should maintain the epoch of the value that we are trying to copy. And epoch is something I added not too long ago that allows me to track where in the execution stack we are. So if we have some compile time execution and we have some runtime execution, we need to make sure that we don't mix up those values. And this is just how it's done. Okay, so we need to have an epoch. I guess we'll need to provide that as an argument for now, and then we'll see later. I could also extract it from the context, maybe. I mean, I already passed the context. It will be easier, I think, if I just extract it from there. So context epoch. Okay, descriptor, we have that. Storage, we have that. Source range, we have that as well. So that seems pretty reasonable. And now what we're going to do is we're going to replace this. Wait, actually, we need one more thing, and that is the value itself, right? That what we're going to initialize. Otherwise, it doesn't work. Okay, now I think it looks good. So we'll do value init. We will create it right on the stack. And it would be even more efficient if I don't zero this out, but I think in the release build it will be optimized away because this is an inline function and the compiler should realize that I'm assigning everything to 0 and then I immediately assign it to something else. If it does become a problem, I can split it into two parts. It's kind of unfortunate that in C you can pass anonymous stack location like this, but you cannot leave it uninitialized, and that's not really great, I think. Okay, so let's see if this works. I have no idea. Maybe I do need to retain this value, but I guess we will see. And now I started a release build, which is quite unfortunate, maybe. Maybe what we will do as well now is we will make a copy of the build.bat and call it release, and actually bring this back to OD, and we will go to release, and that will stay OX. It will only do generate types and build this one with O0 or OK. Actually, I like this. OD. Yeah, that seems reasonable. Let's try to run our new release.bat. Okay, that seems to work. Let's actually try to run our command line test and see if we see any significant improvement there. Well, it's tough to tell. I think we got back 100 milliseconds. That's nothing to complain about. Let's try to run Visual Studio Profiler as well and see how our memory is doing. So memory is still growing quite rapidly, but I think it might be slightly less than it was before. At least it doesn't seem to be, we seem to have everything fine. We can also verify that the executable actually works. It does, so we expected 1 million to be printed out, and that's exactly what's happening. So we haven't broken anything. That is a very good progress. Let's try to convert the other two value any's into this mode as well and see if it helps us at all to make the compilation faster. Okay, let's see. Seems to be just fine. Running our measurement again. Actually, that is not really useful because I haven't rebuilt it. Well, that's pretty good. It looks like we in total shaved almost 200 milliseconds by avoiding this kind of allocation. I think later on I will go through the whole program and make sure that this does not happen. I think that's a pretty good win. Let's I forgot which kind of episode we are on. Let me very quickly check that. As you can see, there are quite a few changes of the project between the episodes, so if you want to follow the progress, be sure to start on GitHub and get updated on that. We have episode 153 before. That means that this would be actually I shouldn't really be committing this stuff. Let's commit it like that. We'll actually disable that test and commit it. Episode 154. Remove memory allocation for result value of math operations. Okay, let's run. No, stop. Okay, it's good that we run the tests, but now I want to re-enable this stuff back. And we're gonna run it again and see what it shows us now. I'm interested in the memory here. So hopefully now the slope will be slightly less vertical, and I think that is true. So maybe, yeah, as you might have noticed, we are now below 1 gigabyte of allocations. That is very good. That means that indeed this stuff was causing some problems. Okay, let's look what else lies in this code path. Or maybe look at the updated profile. I don't know. Still, get by hash is one of the top ones. U64 line is exactly what I was talking about. This is a function that does like it gets the value and aligns it to a specific boundary. A lot of things need to be memory aligned to like 8 bytes or 4 bytes or 16 bytes in the code, and this is what's happening. I might take a look at it. Maybe there is a better way to implement it that will perform better in debug build, but I think the reason we see this actually because of the measurement. It will get aligned and optimized in the release build, and this is why I'm saying that profiling non-release version is slightly awkward, but it is what it is. Okay, what is happening here? Well, parsing takes time, and we still spend a lot of time in talking Eval Operator. We can get a look at exactly where, and it looks like we are spending lots of time in token handle function call, but at the same time, this handle function call does not spend lots of time in itself, so it has very low self time. Match call arguments. Yeah, that's the stuff that does recursive parsing. Okay, so that's actually doesn't make much difference. What else can we see? Handle operator does some stuff, but not too much. Let's just sort it by self time and see what happens. Yeah, this one maybe we'll look at a bit later. I'm a bit suspicious. So either my hash implementation is terrible, which is very probable, but I would still expect it not perform so badly, but maybe it is. This one, yeah, we can't really do anything about it. This just doesn't make sense. This is some debugger stuff. Eval operator is what we just looked at. It has actually quite a lot of self time, so let's look at that. Okay, so I was actually wrong, and each of these comparisons is not very fast. Let's just put it this way. So maybe I would want to optimize this as well. But since I'm going to change how the dispatch happens at all, that's probably not necessary. Okay, these are helper functions. I can't really do anything with this value image. It is about as fast as it can. It does some string equality, and again, I think that in optimized build it's not as bad as this. Value is a symbol, right? This also happens in here a lot. I think it is probably this jazz, but it should also be optimized in production build, so nothing really interesting. Anti-kernel, that is probably memory allocation because we rely on the system quite a bit to do the virtual memory handling for us. Yeah, as you can see, slice equality is here as well. We have assignment, doing a bunch of stuff. Is there anything that is suspicious here? Not really. What is this external code that spends also 200 milliseconds? I have no idea. It also might be that this is has to do with virtual memory, but it's tough to say. There's a bunch of allocations, and I think I can do this view in color collie, and we can see who called it. Okay, can I see who called you? Okay. Oh, interesting. I know. Right. Need to get used to how to read this stuff. I'm not very proficient with Visual Studio Profiler just yet. We are creating a bunch of 64-bit immediate values. We are creating a bunch of literal number values, which seems to be stressing the memory quite a bit. Right, so I think if we continue down the path of trying to not allocate memory, this will make the compilation much faster. So let's just take a look at what Flask does. This in here, and let's just read through this function really quick. It checks that both arguments are integers. That makes sense. And then it does the constant folding, and I think that is actually what is like all of the code goes through here, I would expect. We can try to verify that. Functions, they're like a plus. Yeah. So it says that we only spent 83 milliseconds, so I guess the total time spent inside is actually quite big, but self time is quite small. So let's take a look at what's happening. Right, so we are spending all of our time here in maybe constant fold, but the question is, what is taking so much time here? This should be relatively fast. Maybe constant fold internal. Okay. Right. So we are again, I think, have a problem with allocations. This one is a bit more complicated to solve than the other one. I wanted to do it for a while, but it is a very annoying refactoring that needs to be done. I think what we will do now is I will show you what the refactoring is, and I will try to make it fast. If I realize that it will take too long, then I will do it offline, but at least I want to explain what is happening there. So if we go to generated types and we look at the storage to see what is this immediate. So previously when you would create an immediate that would put it directly into the struct. But now all immediates are turned into static values, and instead they point to some memory that is created on a heap. In our case, in the arena that is used for all the locations of the compiler. This is very, very inefficient for small values. For anything smaller than 8 bytes, it is just wasteful flat out. And for, I think, anything up to 64 bits, we should just inline here. And that means we will have to go through all of the usages of this and verify that they will use a helper or a getter sort of function that will check if the memory is in line or if the memory is somewhere else. This also might be slightly dangerous if there are places where we expect this thing to be on the heap, like we are retaining a pointer to it or something like that. So yeah, but this is what we want to do. I can try to look if that is at all reasonable, and if it isn't, we will go from there. So I would say static memory. We'll say how should I organize this? So we need to be able to distinguish a pointer and an inline value. I could do something really tricky, like I could check the highest bit or something if it's set or not, but let's just do the simple version first. So we'll say the 64 is heap, and the reason this is U64 not bool is because all of the structs here need to be aligned sorry, not aligned, they need to be packed. So you should not have gaps between them, so we can use memcompare more efficiently. So the is heap, and then we need to have a union. I guess, well, I guess let's actually do the union right away. Maybe. Wait, I'm a bit lost. What happened? We're here. Static memory. We'll have an inline one, and here I would have. I don't actually have a way to create raw unions, so let's do the full thing where I would do like S8, S8, and S8. And we can have more of them. So we have 16, 32, 64, we have U8. Actually, let's copy it like this. U, and U. Okay. Right here as well. And I should have copied after I actually changed the sizes, but well, now I have to do it here. 8, 16, 16, 32, 32, 64, and 64. And then the last one is, let's call it heap. And we will take this memory, we'll put it in here. And we'll say that static is, or let's call it heap pointer. That's fine. We static memory, and that is memory. Right. Okay, so these are now going to be stored inline, and if it is anything bigger, it will be stored somewhere else. If I try to build all of that, actually this needs to go away. If I try to build all of that, we'll have lots and lots of errors, but we can at least try to look at them. Surprisingly, there are none in this file. Let's see what is happening. Cannot convert from descriptor star. What is the problem? Static memory. Does that help? Cannot convert from descriptor star to static memory tag. Something is not really working with the generation, and I'm not exactly sure why. Oh, I think I know. I think I know what is the problem. That we need to go to types.h, because here we have, yeah, exactly. We are putting descriptor right here, but instead now we will need to say that tag is static memory tag heap, and then we say heap pointer is descriptor, something like that. Okay, right, this is much better. Now we can go from there. Good. What do we have here? And this is exactly the place where we would save on allocations. We don't want to allocate 1 byte of memory. Instead, immediate 8 will not take an allocator anymore, and it will not memcopy. And instead, we will just say that the tag is static memory tag S8, and S8 this is slightly awkward, but because this code auto-generates, I can't do much about it. I might say S8 value, maybe. That would be slightly better than what we have right now. So S8 value is value. Actually, we are getting a U8 to here, so let's call it U8. In reality, I need to update these functions, immediate 8. They no longer do exactly what I want them to anyway, so it will be a good update. So let's can also put them in a macro, since I have to update all of them at once right now anyway. Let's make define in x, and it will get the bit size. What it will look like is it will be like this. We will put bit size in here. We will put bit size in here. And in here. And in here. That seems right. I need to fix up the macro stuff. And then I can do define imx of 8, 16, 32, and 64. That should be good. Let's see how it is. Okay, all of this seems to work. We also don't need an allocator here. Okay, that goes away. Right. This is a function that compares some static values, and it understands that we know what is the type of those values and compares them. Like if it's a struct, it goes through each of the fields of the struct. If it's an array, it goes through each of the items of an array and recursively and so on and so forth. So it's like this comparison function that I wish C had for us, but we can do it ourselves, at least for the values that are part of the compiler. And it originally wanted a pointer, but now it is not one. So what we want to check is that there is one more assert here now, that static memory tag is the same between these two. And if it is the same, we can actually switch on it, right? And we can do the following: static memory tag u8, right? And then we say return a storage static memory u8 value. Maybe I do have to put it in a new line. So that is the same as the one for the B. And obviously we have to do it now for all the sizes. This is why this kind of change is quite annoying to do, and IDE refactorings also will not really help you here. You just have to sort of type it out, at least in C where there are no generics or anything like that. Okay, static memory tag heap. We take this stuff and in default case we would return false, but actually we will panic and say that we have no idea what the tag is. No, or unexpected static memory tag. Okay, and here we say heap pointer, heap pointer. Okay, how are we doing? This needs to be double equals, not single equals. Right, making progress, not too many left, so hopefully we can make that happen. This is awkward. I think we'll have to copy paste this, unfortunately. I will. Oh, there is this fix me, so I will need to look into the here eventually anyway. So for now, I guess we'll just have to do that. A storage like this. Need to update the variable. And also need to update what we are doing here. So this was doing mem compare. This will be a way longer compare. So let's reformat this just a bit. And we need to add this .heap.pointer. I think that should do the trick. Okay. Storage dot. Okay. In here, we can actually check that it is always on the heap, and that should be fine. We don't need to do that switch. Memory tag is static. And I can do heap pointer. Okay. That's good. That is sort of the same deal. I might actually decide to put number literals to be in line as well, as they are quite prevalent in the compilation, but that can be a separate step. Let's first make sure that this actually works correctly. Did I fix the other one? Right. Okay, should be fine. What else do we have? Storage. Right. Okay, we're building. Cannot convert from number literal star to static memory tag. Right. So that is probably this macro that we have. We can look at. Okay, what's happening here? Right. Storage, static memory, offset. I think we should expect here to always be on the heap. So let's try to do that. And if it is not what actually happens, then, well, we'll deal with that separately. Okay. Static as C-type internal. Great. So this is a getter I'm using to actually extract the value, and this is the one where we will need to do the same switch as we did in storage static equal. So these jazz needs to happen in here. So that actually should be named storage, not operand. That's remnants of some old code. It is no longer there. Storage, okay. Right. Here I was a bit overzealous with removing stuff. Actually, no. So it's a heap. This is what we do. We do operand, static memory, heap. Right, this is why it's a problem. This function, it returns you a pointer, so it will potentially point to a local value, which is not particularly great, but let's see if our code actually relies on that or not. Heap pointer, and here I can say u8 value. This is the dangerous part. Let's see how we do. 64, 32, and 16. In reality, it doesn't matter really which one we take because they all will point to exactly the same place, but that's better not rely on that. Okay, that is taken care of. What is happening here? Right. Define storage static bytes. Ooh, ooh. So, right. I have to change how this works. I think this will have to become a proper function. So something like static inline storage static bytes. There might be a problem where I might be using this somewhere in a constant context, in which case the function will not work. But that is not static data, static value. No, static value is too ambiguous because we have a type called value. What should I call it? Whatever. We'll call it internal for now and then go from there. All right. And this thing, it will accept a void star value and u64 size, byte size. So byte size goes in here, but with the value, we again need our giant switch. Right. So only what we are switching on is now the size. And depending on the size, we will just inline the value. static memory heap pointer. So let's actually do it like this. We create the value here. And we return it here. And in these cases, we'll just assign whatever we need to result. Right, something like that seems fine to me. So 1, 2, 4, and 8 bytes. We have U8 value, and we will cast this to U8 star, and then do star. Something like this. 64, 64, 32, 32, and 16, 16. Okay, something along these lines. Let's try to do this. And then we'll go from there. So this file now builds, but we might have other problems. Right. Okay. In here, we are casting one integer to another, so we also have to be very careful with the size. But I think I can do it like this. I can say U64 byte size is this, and then I will say storage static internal, so I will call it myself and provide memory and byte size. Something like that. Okay, let's realign this stuff slightly. Good. Next. Right. This is gonna be the most painful one, I think, because what this is doing is it takes a value that we statically known at compile time, and then it copies into a read-only memory of the executable. And that requires it treating it like this. Well, I guess let me look into here just a second. Right. So it knows the byte size. And what we can do is the following. We can switch on the byte size and in here assert that the tag is actually what we expect it to be. I think that might help me do what I want to do. Okay. 1, 2, 4, 8, 64, 32, and 16. now I should be able, okay, first let me check that I haven't screwed up this. I did. Static memory. Default. Okay, so that is that, and now we should be able to do the following trick. We will pass the storage in here, and then we'll just take the byte size from the storage. Okay, that is pretty good. Okay, in here we should be able to use storage static internal. Maybe I should call it something better than that, but we'll see. Result and result byte size. Right. Okay. What's happening here? Here we are dealing with field access on the static values. So we have something like, let me show you. Maybe not here, but here. We have this message, which is a static string, but it's actually a struct with two fields. One field is bytes, the other one is length. And when we do this access, this is exactly what is happening over here. And this is quite interesting. So I think for now, I will expect structs to always be in the heap and larger than 8 bytes, which is kind of awkward. So this will be definitely a fix me. So if field storage static memory tag is not static memory tag heap assert or panic fix me support this. I don't think that's the case right now, but it definitely can be that we will have structs smaller than 8 bytes that will be stored in line. Maybe I have to be very explicit that not automatically all values are stored in line, but only like integers or something, or primitive values. So I still need to think about the best semantics here, to be honest, but that's should do the trick for now, I think. I'm just trying to get it to compile because, as I mentioned, this is a pretty tedious debugging, tedious refactoring that has to happen here. Okay. Right. Well, here we can use storage static. What did I do in the assign example? Here. Yeah, storage static as C type. Where was it? Here. That's not called source. That is called. Wait, where is it? It's called value. It's called value. Great. Okay, just a few more. Right. That is easy to fix. We'll just need to wrap this in storage static SC type, and it's even more safe than it was before, so that's a good improvement, regardless of what else happens. Okay. Who else is unhappy? External symbol, that is the same sort of jazz. We take function body, like so. Does it work? Looks like it. And probably there are a few more. Cannot convert static memory. Right. Storage, static memory. What's happening here exactly? So this copies. Okay. Right. So this is the same thing where we just rely on whatever the byte size is. Okay. Looks like the last one. Okay, and this is should be easy. Okay, doesn't look like that's all. Yeah, now compiler is very angry at us that we actually have also all of these S types, and for now I'll just not do that. I might still bring them in, but that's not important at the moment. U64 difference, right? Uh, Media 64 no longer needs the allocator. Okay. U64 different. So somebody else is unhappy about the allocator. Define compile time function. I mean, I did fix this. Okay. You're right. We also have the bunch of helpers that are value from blah. So this needs to go. And almost done. Bunch here as well. If it works, it's going to be a really good change because it will really improve the performance of the allocation, as we will have a bunch of stuff in line now. But if it doesn't, we'll probably see very weird crashes where we are retaining a pointer to some value that we shouldn't really be retaining a pointer, and that's gonna be pretty bad. Okay, right, a bunch of them here. Right about now, I wish my editor had regular expressions, but not yet. This is no longer leaking, which is very good. Okay, we also have context allocator stuff. What else? Since this function, and this is sort of the reason why we got into this refactoring journey in the first place, because this function was calling these functions which were doing the allocation. Right. Just before. Okay, temp allocator, temp allocator, more of those. Okay, let's see. Okay, we are building. That is a very big milestone. Let's re-enable all the old tests and try to run them. If this works the first time, that would be amazing. Fortunately, it does not. So somewhere where we were expecting to have a heap value, we did not get one. Okay, let's turn off the profiling and let's just run this. Okay. So what is the size? Byte size is 18, but for some reason that storage tag is not. Somehow we have U8. That is very suspect. Symbol. Okay. Interesting. Value as symbol. What are you doing? Are they defined? Yeah, right. Right. These are defined as helper and they are inside of value.c. Okay. What are these things doing? So we have C type, this symbol, it checks that the value is that thing, and then it just puts it. Okay. Token make symbol. I think this is where we are creating those. And this is where things I think are going wrong. Let's stop there and see how it is. Okay, so we have symbol, right? And we are going into here. Byte size is 18. Go in here. Wait a second. Right. This is where things go wrong. So let's fix that. And the issue is I'm checking the byte size and I'm setting the right field, but I'm not actually setting the right tag. Tag is static. Tag u8. You know the drill, 64, 32, and 16. Right. Let's try that. Run it again. Let's see what is in our symbol. No, not symbol. I'm interested in value init internal returned storage. Yeah, we are saying that it is heap storage. Okay, let's let it run. Okay, we did a bit of progress, I guess, but not much. Sort of the same issue. We got a heap value, but we were expecting to have a non-heap value. Okay. The byte size is 8, so that makes sense. But who actually got us here? Static value up to 64. Okay. Storage static. Okay, so we are looking at the precedence value. Okay. Token value force immediate integer. I guess this is where things happen. Okay. Let's look at this stuff again. We shouldn't really allocate here. That's, I think, the first thing. We can pass this directly, but digital cast result. Okay. Let's just look at this function in the debugger and see what is exactly is happening. Okay. Going here, going here, going here. Bit size is 40, it's 64, I guess. Yeah. The value is 16. Okay. byte size is 8. That makes sense. Let's step into here and see what's going to happen. Right, okay. Again, the problem isn't exactly the same function, and the problem is I forgot the breaks. Pointer mismatch for actual parameter. Right, we want it like this. Again. Okay. Well, that is quite a bit of progress. So we made it through a lot of the functions. Let's see where we are now. First of all, what is this test? We are testing external functions. Right. Encode instruction assembly. And what is the issue exactly? Storage memory tag is U32. Okay, so byte size is 4, but we got something completely different in there. Interesting. And what are we trying to encode, I wonder? How is best to look at this? Instruction assembly, type assembly, okay. Assembly, mnemonic, operands. So this is unsurprisingly a move. And if I look at the compiler source location, it tells me that this is line number 264. 264. Let's go and see. So it is, yeah. As expected, this is where the problems can happen. I guess what we need to do is we need to say void star memory is like this, and then adjusted source would be storage static internal, and then we'll accept memory, and then it will accept chunk size, something like that. I would guess. Let's try again. Okay, that is even further. We are now getting to the big examples. So I think this is Hello World that is crashing. Okay. The same thing. Value up to 64. Storage different byte size. So yeah, it expected it to be U64, but I assume that it is heap. Right, okay. Can calculate value, right? Okay, what is this value? Source value, source range, and size. Right. Okay. Mm-hmm. get filled or something. Right. So I was feeling icky about this when I was doing, and it is indeed the source of the problem. But now I know how to fix it because it is exactly the same fix as this one, more or less. Okay. Field storage. Okay, this is no longer required. The byte size goes into here. And as far as the memory goes, we take that out of the storage. So storage, what's it called? Storage static SC type internal. We would give storage, and we would also say that storage byte size. Okay. Hopefully that's what needs to happen, but I'm not sure. One more time. Okay. We are no longer crashing, but at the same time we are also not compiling it correctly, which is not good. Assertion failed static pointer. Right. This is awkward. Okay, I know what's happening, but I'm not gonna actually fix it on the video. This has to do with this thing where we are dealing with strings, and I'm not happy how we are doing it right now. So I think string literals are gonna change internally, and that's why I'm saying, like, I'm just gonna ignore these two tests and go and fix them after finishing the video. So we'll disable the fizzbuzz. I still want to know what is wrong with hello world. All right, large executable or an executable with a lot of constant faulting. Okay, which tests are failing again? So this hello world that fails, and it fails because we cannot match a right file. I think it is in the same category, so it just doesn't know what to do with this stuff. And the solution to this, well, just out of curiosity, if I do it this way, how many? I think it is 13. Whatever, for now, let's just say 10. Right. Yeah, it is 13. So the problem is with the handling of the stuff. The question is which part? Is it the bytes that are screwing up, or is it something else that's screwing up? I think it is the bytes. Yeah, yeah. So message length. Does it work? Yeah. Anyhow, so this is busted, but it was a bit of a hack in the first place, so I will go and look at it separately. For now, let's get back to our main course, which was did it improve the performance of the constant folding? It should, because we're no longer be allocating so much, but let's take a look at the profile. Yeah, this is definitely growing slower than before. So yeah, we saved about 200 megabytes of memory, which is 1/5 of what we were allocating at all, and that's quite a lot of memory. So that's very good. Let's do release build and see if it helped with the performance at all. I don't actually think that is much better than it was before, so it doesn't look like this was problematic in terms of performance, but at least it didn't hurt. It saved us, as I said, a fifth of memory, which is a win in my book. And the whole situation with the static strings, that's something I can fix and I should fix. I think that it's wraps apps what I wanted to do for today. There is definitely lots more to check, optimize, and verify. But for today, that's all. Thank you very much for watching, and hopefully see you next time.